Well, last week we learned about a energy bands and their existence, and we talk about the movement of a conduction band. We can call it a current flow in semiconductor. Okay, generally we know about a current density as Qn nu E, and they can expressed as a power, a mass product, a velocity. Now velocity we can say a drift velocity. Drift velocity can define as a carrier's mobility and to ability to move, which means a voltage, electric potential energy. So if we gather this drift velocity and about definition of power, we can define as carrier's mobility as with mass of carrier and charge of carrier. And here there is a drift mean free time, which means if carriers are in conduction band, they will with no voltage, with no potential energy, they will move like here on going nowhere in wandering. But if we give this a electrical potential, now electrons will have some directions. So by this on Brown motions, and they will have a tendency to have go plus to minus if electrons. Holes otherwise they will move minus to plus. Okay, so we talked about a current flow in semiconductor. So let's move on to the total carrier drift. Okay, there is some carriers that can conduct to one place to other place. It is on plus there is a hole, and on the negative and there is a electrons. So the ability of a carriers to how much they can give a current defined as here, ability of negative charge and positive charge. Now we're going to some mathematics, the definitions of electrical potential and a current flow and resistance. So now using this combining those three equations, we can know about this a current density. It is the same way as we said about earlier, and it's a difference between a excess. In here we can know this potential and current. It can be known as experimentally. On here we can use this some mathematical problems. So we learned about how they move on the conduction band on electrons and valence band on hole. We know about how they would move and their amount of carriers. So now we're gonna talk about they can be what conditions have for electrons have resistance. So what could be resistance in the semiconductor will be about here. It will be mean free times. If mean free times gets larger, it will be a current will be go down. So there is a ionized impurity called if a donors can be sabotage this flow. If it's a donor, will be move like here, and if the acceptors, they will move like this. And there is a lattice scattering. A non-vector energies like a thermal energy on systems can tremble this whole lattice. So the energy bands can be a up or down, can be get distracted. So energy means a on quantum physics, energy is a product of h bar and k over 2m. M here will be a mass of electrons or carriers. So if energy modulates the carrier's mass, then it will be the drift velocity can be varied, and there is a soft surface roughness scattering. That is the semiconductors can be rough because they can be like a flat. So they can bring this here. The surface is rough as here, then the energy diagram can be like here, like bluff. Some point can be up, or some point can be like there. So a conduction bands can be various. So to move here to there, can be a energy loss, unwanted energy loss. So combining all of these, we can find that temperatures, relationship between temperatures and mobility in here. So we can know that as temperatures go higher to high, then will be mobility can be down because of a lattice scattering. And if temperatures go down and down, there will be also down for mobility, which means a impurity mobility.